Okay, welcome back. Now we can start discussing an expansion of Fourier series topic. The expansion is the determination of Fourier series representations and the coefficients for discrete time signals. So the new topic is discrete time Fourier series, DTFS, we can abbreviate. If you remember the Fourier series concept, the Fourier series representation is available for periodic signals, right? We have to remember this. And for continuous time signals, for continuous time periodic signals, in the case of continuous time, we have this kind of a representation. X of t is equal to k from, let's say, minus infinity to infinity, c sub k e to the minus j k times a fundamental frequency. Let's call it omega 0 t, where omega 0 is 2 pi over capital T, where this capital T is the period or the fundamental period. So this was our representation for continuous time. Now, if we try to do it for discrete time signals, let's try to convert it to a discrete time version. We can have x of n, a summation over k, but I'm not indicating the limits of this summation right now. Again, let's say c sub k e to the minus j times k times omega 0, and for that omega 0, I'm going to write it as 2 pi over capital N. That is the fundamental frequency. 2 pi over capital N. Capital N is the fundamental period, but we have to be aware that capital N is an integer number, because a period, the period of a discrete time periodic signal must be an integer. You cannot have a period of, let's say, pi, okay? Because then it means that for no rational multiple of pi, you can have the same integer number. It's impossible because it's irrational. It's not in the form of a ratio. And then instead of t, I write n. Okay, I write it like this. Now, when you focus to this portion, okay, k times 2 pi over capital N, we immediately notice that when, for example, k becomes capital N in the during the summation, if k is equal to capital N, that would make 2 pi, because it would be capital N times 2 pi over capital N, that is 2 pi. What is e to the minus j 2 pi n? N is an integer, okay? That is e to the minus j 2 pi. It's the same. Or 2 pi times 2, 2 pi times 1 million, they're all the same. It is equal to 1, okay? When you go to k is equal to capital N, you reach to something equivalent to e to the minus j times 0, which is also 1, right? E to the 0 is 1, e to the j 2 pi is 1, e to the j 4 pi is 1. So k is equal to capital N is a critical position, which we can denote as coming back position. Or let's say, let's think of another example. When k is equal to n, then e to the minus j times n times 2 pi over n times n is equal to 1. When k is equal to n plus 1, what do we have? Let's also check this one. Then we have e to the minus j n plus 1, which is k, actually, inside the summation. I'm thinking of individual terms here, times 2 pi over capital N n. Now, this can be written as e to the minus j n times 2 pi over n n times e to the minus j 2 pi over n times n. I can expand the exponential term into two multiplicative terms like this. And we know that this is 1. And this is the same as having a k that is equal to 1. Now, so when k is equal to capital N plus 1, it's the same coefficient or harmonic as saying k is equal to 1. It corresponds to the same. When you write k is equal to n plus 2, this time it would be equal to having k is equal to 2. So you can say that n is equivalent to 0. N plus 1 is equivalent to 1. N plus 2 is equivalent to 2. And it goes on like this. In fact, 2n plus 3, for instance, is equivalent to having only 3. So the harmonics are repeating themselves. They have a period by themselves. Harmonics are repeating themselves. So if you have an infinite summation, that's why I didn't write the summation starting and ending points like from minus infinity to plus infinity or anything like that. I didn't say that. Since harmonics are repeating themselves, we cannot have infinitely many of those things. Otherwise, it will diverge. This summation does not converge for k from minus infinity to infinity, because it's also periodic by itself, and if you accumulate a periodic sequence, it will diverge. So we have to have a summation only within one period. So the true representation is like, for example, k from 0 to capital N minus 1, where capital N is the period, of course. C sub k e to the minus j k 2 pi over capital N n. This is, in a sense, the Fourier series representation. So the Fourier series expansion, or the highest frequency harmonic, for example, the harmonic of the highest frequency, which was infinity for continuous time signals. We could have C infinity, C sub infinity. It may be decaying in value, but we have infinitely many Fourier series coefficients. Fortunately or fortunately, we don't have it in discrete time signals. We have only capital N distinct Fourier series coefficients within one period. And the Fourier series coefficients afterward repeat themselves. For instance, we can say that Cn, which doesn't appear in this summation because k is from 0 to capital N minus 1, only within a period. We don't have capital N. So C sub capital N does not exist, but that is exactly the same as C0. And Cn plus 1 is the same as C1, etc. It goes on like this. So the Fourier series coefficients are that way. Or, in a negative sense, you can think of it like this. C minus 1, for instance, is essentially equal to C capital N minus 1. Or C minus 2 is equal to C of, capital N minus 2. And it goes on like this. So the negative Fourier series coefficients are just the end of the Fourier series coefficients. They are the same. Which also converts this into one final expression, which is the one that we are going to use all the time. And I have to explain what I mean by that. That is equal to x of n is equal to summation k within a period of n. I indicate it like this. C sub k e to the minus j k 2 pi over capital N n. So this is the formula. Notice that I put k is equal to in greater and less than signs in between them an n, capital N. That may be from 0 to capital N minus 1, which is containing only n samples, or it may be somewhere from capital N over 2 minus capital N over 2 to plus capital N over 2, but you have to be careful about how many terms you are containing inside the summation, and the number of terms you have to contain in the summation must be exactly equal to capital N. For instance, if capital N is 8, I cannot say that it is from minus 4 to 4, because from minus 4 to 4, the summation includes 9 terms. Be careful about that. From minus 4 to minus 1, there are 4 terms. From 1 to 4, there are 4 more terms. And at 0, there is 1 extra term, a total of 9 terms. But you have to have 8 terms. So you can write it like from minus 4 to 3, or from minus 3 to 4, from minus 2 to 5, just 8 samples, just capital N samples must be contained inside this summation. This is the Fourier series expansion or the representation, Fourier series representation. It's this. And now from here, it's also critical to come up with a formula that would give us what is C sub k. Okay, what's the Fourier series coefficient? It's possible to obtain this by multiplying the left-hand side of the equation and the right-hand side of the equation with another discrete time complex exponential, and then sum up at both sides and come up with an expression which will give you 0 at the right-hand side and etc. That will isolate CK. I recommend that you may consult to Oppenheim's book in that explanation. If you are interested in how to derive CK from this formula, how to isolate CK. We did this for continuous time. Therefore, I don't really want to spend time for the derivation of CK from here. But as a result, the result is something that I can say. It's a Fourier series formula. It's 1 over capital N summation n within the same period. So the same kind of summation is necessary here. X of n e to the excuse me, I have been doing a mistake from the beginning. I will correct it. Here it's minus j k 2 pi over n. I will correct it with red marker. The expressions that we have been using here are all positive. E to the not minus j k 2 pi over capital N, it is e to the plus j because it was a plus here as well. Okay, so the Fourier series representation requires positive complex exponentials. Exponent is positive in angle, and when you extract CK, that is the one with a negative exponential term like this, a negative in the exponent. So please correct your notes if you're taking notes. And this is the formula for determining the Fourier series coefficient. So knowing this and this will help you to determine the Fourier series representation and the Fourier series coefficient. So these are the Fourier series coefficient. This is the formula that gives you the Fourier series coefficient. You may use this formula in case the shape is non-sinusoidal in discrete time, like a rectangular pulse train. Of course, these are discrete time signals. Be careful about that. I don't mean rectangular boxes of continuity that we did for continuous time Fourier series. This is like some bars and then some zeros and then some other bars and then some zeros, etc. And you can use the formula to find the Fourier series coefficient. Similar to what we did in continuous time, we are not going to use the formula all the time. We will use some properties, like the properties that we have been using in continuous time. Similar properties exist for discrete time. And if it is in the form of a sine or a cosine or something like that, trigonometric styles are used or expressions are used in your formula, then you can use the Euler's formula, of course. You don't have to consult this cumbersome summation for determining the Fourier series coefficient if it is already a cosine or a sine or something like that. So now we can start seeing some examples, and the examples will start by simple sinusoid. And if it is sinusoid, of course, we don't use the formula. We use the Euler's expression. Let's say x of n is equal to sine what? Sorry. Sine omega 0 n, for instance, where omega 0 is, of course, it's equal to 2 pi, it's equal to 2 pi over capital N. You can use the Euler's expansion to expand the sign in terms of 1 over 2j e to the j 2 pi over capital N n, and minus 1 over 2j e to the minus j 2 pi, behaving funny today, 2 pi over capital N n. And from here, we can see that this is a harmonic for k is equal to 1, and this is a harmonic for k is equal to minus 1. So we say A1 is equal to 1 over 2j. Come on, 1 over 2j. And from here, we can see that A minus 1 is equal to minus 1 over 2j. Okay, very similar to what we did for the continuous time Fourier series. Now this these can be the unique Fourier series coefficients, but I may want you to plot it on the Fourier series coefficient axis. And we found only two coefficients, A1 and A minus 1. But I also said that the Fourier series coefficients are also periodic. They are repeating themselves. So depending on the value of capital N, the way to plot these would look like this. Let's say this is K, and these are CKs that you're writing. As we see, it is 1 over 2j here. Let's give a value of 1 over 2j. I'm sorry for the representation because it's complex, and why am I putting it like a bar over there? But let's take a look at the magnitude, and even the magnitude within the sign. Like I'm going to indicate minus 1 over 2j like this. Okay, so these two Fourier series coefficients, let's say that we are able to represent like this. This is 0, this is 1, this is minus 1. And let's say that this is n. Okay, notice that n is the same as 0. So at n plus 1, we have, again, 1 over 2j at n plus 1, and minus 1 over 2j at n minus 1. Because n plus 1 is the same as 1, n minus 1 is the same as minus 1. So we have these, and then we have the repetitions of that here, 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 etc. So those plus and minus signs are just repeating themselves with a period of capital N on the axis of K, the Fourier series index. It's also possible that in a question, you are expected to indicate the actual result in an analytical form. These are the graphs that you have to provide us with. You have to give at least a few periods of the repetitions to show that everything is periodically repeating in the Fourier series expansion. But if you want to write it in an analytical or mathematical expression, then this would be only half correct. You have to indicate the periodicity as well. And how can you do that? You can do it like this. You can say A sub K times N plus 1 is equal to 1 over 2j, and A sub K times capital N minus 1 is equal to minus 1 over 2j. So if you put these expressions into a box and tell me that these are the Fourier series coefficients, you will get 10 points. If you say A1 is 1 over 2j and A minus 1 is minus 1 over 2j, you will get, I don't know, 3 points or 4 points, whatever. Although it's correct, it doesn't express everything, because for all k, integer k, and if the period is capital N, you have to express it in the form that is boxed inside a red box. Okay, that's the proper way of writing the expression. So just remember this all the time. You find the Fourier series coefficients, and then you say that k times n plus the index that you find is actually valid as index for all the values. It's not only for the Euler's expansion, it's valid for all the Fourier series coefficient representations that we found before. So let me go back one page here and write a final expression like this. See r times n, where r is an integer and capital N is the period, plus k is equal to 1 over n, and within a period x of n is the minus j k 2 pi over capital N n. Now this makes the best sense. Don't simply write it as c sub k, but it's also valid for all the periodic expansions of it with multiples of capital N. All right. Well, we can come back. Another example that we can see, let me open a new page. Another example is another sinusoidal thing, which where Euler's expansion is available. X of n is equal to 1 plus sine 2 pi over capital N n plus 3 plus 3 cosine again 2 pi over capital N n plus cosine 4 pi over capital N n plus pi over 2. this is a semi-hard question. It's not a hard one because at least the first sine and the second cosine are having the same periods, and the determination of the fundamental period, hence the fundamental frequency, is not a big problem here. But of course, in an examination like the one that you have encountered, it may be like pi over 5 and 2 pi over 7, for instance, as the frequencies of the sine and the cosine, two additive terms, and then you have to find the common period and the common fundamental frequency, where each of these must correspond to a frequency that is an integer multiple of the fundamental frequency. Okay, but here the question is a little bit easier in that aspect. You can write this in the form of an Euler expansion, and that is 1 plus there is a 3 cosine, and there is also a 1 times sine at the same frequency. So let me combine those, like 3 over 2 plus 1 over 2j as the coefficient of e to the j 2 pi over capital N, and like this. And then I can write their conjugate parts, 3 over 2 minus 1 over 2j e to the minus j 2 pi over capital N, and that would handle this part. Now I have to write the parts corresponding to cosine 4 pi over n plus pi over 2. Maybe I should write it underneath like this. That is 1 over 2 e to the j pi over 2. That is when you expand in the Euler expansion, there would be in plus e to the e to the 4 pi over capital N plus j pi over 2, and that j pi over 2 I can write it separately here like this. So this is a coefficient times e to the j times 2 times I'm going to write 2 pi over capital N, because it was 4 pi over capital N, but 2 pi over capital N is the fundamental frequency. Therefore, this is twice the fundamental frequency, like 2 times 2 pi over capital N times N, and plus, again, 1 over 2 e to the conjugate, e to the j minus j pi over 2 e to the minus j times, or maybe I can write it like this. It would be even nicer. J times minus 2 times 2 pi over capital N, and like this. So this is the complete Euler's expansion. What are the Fourier series coefficients that we can observe? Let's mark them with red. One of them is this. This is one Fourier series coefficient. The other one is this, which scales the following harmonic. And the other one is this, which scales the other harmonic. Another is this, and another is this. But what Fourier indices, or what series indexes do they correspond to? This is a 0, of course. What is this? 2 pi over capital N is the fundamental frequency, and this is 1 times 2 pi over capital N that we see here. Therefore, the index is 1, and this is A1. This one here is minus 1 times the fundamental frequency, therefore it is A minus 1. What is this one? A sub what? Did I get an answer from one of you guys? You may, yeah, 2. Fatma Nur immediately told me that it's 2 because, as you see, it is 2 times the fundamental frequency in the harmonic expression frequency. So it is A2. And this one is therefore -2, -2, A sub -2. And these are the 5 Fourier series coefficients that you have. You have to consider this kind of an approach all the time, okay, while solving or while expressing the sinusoidal form of a periodic signal using Euler's expansion. Of course, not every sinusoid is periodic. We know that in another example. Let's say cosine n. Okay. The answer that you must provide if I ask you to give me the Fourier series coefficients of this is that you have to say that this is not periodic. If you think it is periodic, I will have to ask you what is the period. And then you will see that in the form of 2 pi over capital N times N expression, where that over capital N is the period, you will find it to be 2 pi. So the period is 2 pi. It can't be 2 pi. It must be something else. So what is it? If it is in the form of a ratio, you can proceed by multiplying with integers to come up or to find the real period. But 2 pi is not rational. It's irrational. Therefore, there is no way that you can find an integer n where this cosine n repeats itself. So this is not periodic. By the way, the other exercise may be nice. Cosine 7 pi over 8 n. I'm not asking for the Fourier series coefficients. Of course, the Fourier series coefficients are A1 is equal to 1 over 2, A minus 1 is equal to 1 over 2. Because there are only 2 Fourier series coefficients and there is a fundamental frequency, etc. There's a fundamental period. But the question of interest would be perhaps to ask what is the fundamental period? Not the Fourier series coefficient. It's boring, but what's the period? Now, think of it like this. You have to write it in the form of cosine 2 pi over capital N. Right? So what is this capital N here? 2 pi over capital N is equal to 7 pi over 8. So capital N is equal to 16 pi over 7. Okay. This is what, sorry, there's no pi. Excuse me. Okay, it's 16 over 7. Now, what kind of an integer number is this? 16 over 7 is not an integer, but it is a ratio of 2 integers. It's in the form of a ratio. It's a rational number. And for the period, this rational number can go up to an integer by multiplying this with another integer. So the period is like r times this capital N, or r times 16 over 7, which makes an integer. An integer. So what is r here? Of course, the denominator. After all the simplifications, the denominator that you will find will be the thing that you have to multiply. So when you when we multiply with 7, the period becomes 16. Okay. So the period here is not, of course, 16 over 7. It can't be. It's not an integer number, but it is 16. This is the fundamental period. Then the frequency, the fundamental frequency that you will find will be 2 pi over 16, which is pi over 8. This is the fundamental frequency. Now let's come back to the question. X of n was equal to this in the question. And I was asking you the Fourier series coefficients. If you fail to find the fundamental frequency or the fundamental period, you would say it is 1 over 2 and 1 over 2, which is kind of correct, but what do the indexes correspond to? And interestingly, the indexes would correspond to the fact that this 7 pi over 8n is 7 times pi over 8. Okay, so it's the 7th harmonic that exists in the question. So A7 is 1 over 2, and A minus 7 is also 1 over 2. Okay, it's not A1 and A minus 1. It's A7 and A minus 7, because the fundamental frequency is pi over 8, and the fundamental period is 16 for this signal. I have to confess that this is very detailed or very technical. And where do you encounter such situations in real life? Well, you don't encounter those things in real life, but examinations are also real life situations. So you encounter such tricky questions in examinations in real life. You have to give the correct answer of A7 is equal to 1 over 2, and A minus 7 is equal to 1 over 2. And if you say A1 is 1 over 2 and A minus 1 is 1 over 2, that would correspond to an incorrect answer. Because you have to see where the Fourier series coefficient is appearing, at which frequency it is appearing. That is a critical thing. And you have to be aware of that. Okay, now regarding the Fourier series coefficients, I will show you only one example, okay? And that one example would be the rectangular box. So I'm opening a new page. We are running out of minutes, I'm aware of that, but since that concludes the chapter, I want to go through this one. So red, let's make it black. I want to go through this example, and after that, I will just say that the properties are listed in the book. They will also be available to you in the examination in terms of crib sheets or cheating sheets. Now, I'm not going into the details of discrete-time Fourier series, because discrete-time Fourier series is very detailed, is covered in very great detail in digital signal processing. So for those of you who are interested in signal processing, will definitely get this digital signal processing course. And over there, discrete-time Fourier series is explained and covered very detailedly. And it also corresponds to something else. Let me write it. Discrete-time Fourier series in digital signal processing is also known as discrete Fourier transform, DFT. They are the same thing. DFT is the computer way of finding the Fourier transform. So, for example, if you're using MATLAB, you have DFT, which has a fast implementation, by the way, also known as FFT, the fast Fourier transform. These are the tools that take the discrete-time Fourier series. In one period, let's say its period is 8, you take those 8 samples, you don't consider it as being periodic, but you only take 8-point signals, and you take the DFT or FFT, if they're the same. It's just the name, the fast implementation is FFT. And those 8 values that you get will correspond to the 8 distinct discrete-time Fourier series coefficients, which are also the DFT coefficients or FFT coefficients. So you will see a lot of DFT and FFT in digital signal processing. That's why I'm not going into the details of this, and I'm not going to ask questions from discrete-time Fourier series too. So after warning you a lot about being careful about what the indices, etc., I'm giving you a relief that you're not gonna come up with any question from discrete-time Fourier series because it's too much detail. We will see only one example, which is the rectangular box shape, like this, whose length is 2n1 plus 1. So this is n1, this is minus n1, this is 0, and we have a lot of ones in between, like this. Okay, it's 1. From minus n1 to plus n1, it is 1. And then afterwards, a lot of zeros come into the picture. And around capital N, which is equivalent to 0, we have some other ones again at the same size. What is going on here? Let's erase this. Okay, finally. Like this. So as you see, this is again with a length of 2n1 plus 1. So the last one here is n plus n1, and here it is n minus n1. And everything in between is zeros, and then zeros, and then the same box, and then zeros, etc. So it's a periodic rectangular box string, but in discrete time. Its period is capital N, and it is non-zero from minus n1 to plus n1. So how can we find the Fourier series coefficients? Let's call them AK. It is, let's write the formula. It's equal to 1 over capital N in a summation. And the summation that I'm going to write, I will choose it to be from somewhere around n over 2 to plus n, minus n over 2 to plus n over 2. So somewhere from here to here. Let me put them in red, like this, from here to here. That's one period I take in a symmetric manner. And in this summation, there's only a few non-zero positions. Those non-zero positions appear when it starts from minus capital N1 to capital N1. Between this range, the summation range, the signal value is 1, and out of it, it is 0, so I don't write them, times e to the minus j k 2 pi over capital N times n. Okay, so this is the summation that I have to evaluate, and this summation is symmetric, but it doesn't start from 0, so I cannot write it in the form of a power series. I want to turn it into a power series by saying m is equal to n plus capital N1, so that this summation now starts from n is equal to 0 to 2n1, okay, and e to the minus jk 2 pi over capital N times, instead of n, I will write m minus capital N1. And e to the minus jk 2 pi over capital N and n1, when you make the multiplication in the exponential term, it will make a separate exponential which is independent from the running index of n, and it can be taken out of the summation like this. There's a 1 over n, e to the 2 minuses cancel, and we have only j, k, 2 pi over capital N, N1, like this. And afterwards, there's a summation, n from 0 to 2n1, e to the minus j, k, 2 pi over capital N, n. Now, this summation is a power series. It's like a to the n, from m from 0 to some number, a to the m. And you may remember what it was. It was 1 minus a to the upper index plus 1 divided by 1 minus a. From calculus, you may remember the summation of a to the n. Let's remember it. What is summation k from 0 to, let's say, n, a to the k? Okay, what is this? It is 1 minus a to the n plus 1 divided by 1 minus a. Okay, that's what I'm trying to say. So I will apply it to here, and I will get 1 over n e to the j k 2 pi over capital N and 1 times 1 minus blah blah e to the minus j k 2 pi over capital N 2n1 plus 1 divided by 1 minus e to the minus jk 2 pi over capital N. Okay, this is the summation. And you can leave it like this. It's a large expression, but fortunately there is a simplification. Maybe unfortunately there is a simplification, and I'm just going to indicate or write down the simplified form. It is sine 2 pi k. Because of the Euler's expansion, it boils down to become a sine in the numerator and in the denominator. N1 plus 1 over 2, but it's, as you see, a little bit ugly, over n divided by sine pi k over n, like this. This is the simplification. Of course, this is valid for k different than 0. As usual, you have to find the DC value separately, because if you substitute k is equal to 0, it would be a sine 0 over sine 0, which is 0 over 0 ambiguity. You can use Hospital's rule, or you can find A0 separately to determine or detect that A0 is actually the DC value, which is 2n1 plus 1, the number of ones divided by the period. So this is A r times n plus k is equal to this, and this is A r times n is equal to A0, it's equal to this. If you can do this and put all these in a box, okay, then that would be the correct answer. And you can see now why I'm not very interested in asking you such exam questions, because they are cumbersome. It requires a lot of computations and things like that, and it is usually evaluated in the computers. So analytical way of trying to find the expressions in discrete-time Fourier series and the discrete-time Fourier transform, I want to leave them to computers. I want to leave the solution to computers for the evaluation. And analytically, it's just too complicated. We will mostly deal with continuous time signals throughout this course. And whenever it's discrete time, we will have another tool, not the Fourier transform, but it's going to be called a different transformation. We will see that. So this is the only example that I want to show you, just for the sake of completeness. You're not very much responsible from these, but you have to know it. You have to be aware of it. So in that sense, you are responsible. But I'm not going to ask detailed questions from discrete-time Fourier series. And for the curious, the properties By the way, I will also provide you with the properties in tables, but if you want to check the book, it's starting from page 221. In Oppenheim's book, just check out the Discrete-time Fourier series properties, and you can also see a few example questions, but I'm not going to ask detailed, specific questions from this particular topic. I'm just showing you this so that you know it, you're aware of it, and that's your responsibility. You have to be aware of it. So let me ask you if you have any questions. If you don't have any questions, that concludes our lecture for today. And starting with the next day, next hour, we will start with the Fourier transform, not the Fourier series, but the Fourier transform itself. Okay, any questions now? Okay, not many questions, I see. So I'm stopping the recording. We will meet on Wednesday, and we will start the important topic of the Fourier transform. Okay? Until then, take care.